was introduced already. But before we get to the presentation, I would like to talk about my background. So I'm an architect, graduated a couple of years ago from Fine Arts in Poznań. I'm a self-educated coder, and for the last 2 years I was working at the Royal Academy of Arts in Copenhagen as a research assistant in the Center of Information Technology and Architecture. So this just sets up the context of this presentation, I think, and I'm a bit surprised that I was invited here as a person outside of the IT community. But I would like to present you my work and also work of other people from building industry and how do we actually use coding in our practice. So let's start with some history. That's more or less how we used to work for a couple of hundreds of years. And you can see that this is these are some drawings from the Eiffel Tower. And it was quite a labor-intensive work to do. So there was around 500 engineers, or actually drawing people, employed in this project for a couple of years. And every detail was drawn manually. So you can imagine it being quite a challenge. And fast forward to the 60s, we introduced Ivan Sutherland with his sketchpad and light pen. So I would say that this is the beginning of the CAD era, so computer-aided design. And you can see that this is the first kind of human machine interface where you actually operate with hand drawing on the screen rather than actually typing something in or using punch cards, right? So that's year 63, and from that moment, nothing really changed much. We just got nicer offices with nice posters and a lot of computers, but the principles are basically the same. We operate with computer using some visual interface. We draw the drawings. This time we can, let's say, delete and copy more elements at faster pace. But more or less, it's basically the same as we did with the Eiffel Tower. We were drawing it manually on the screen, on the paper. Now we are drawing it on the screen. So what happened next? We came out with some kind of ideas for what could be done better, what could be done faster. And before we get to the actual topic of this talk, we'll just talk about the theory. So we'll be talking about parametric models, but before we get to the parametric models, we'll just ask each other, what is a model? So in this context of this presentation, model is a system which describes some part of reality by setting up the relationships between them and some kind of properties of the reality. And in terms of architects, we are talking about parametric models. Parametric means that the model is able to change its properties based on the parameters. So here we have one of the first examples of parametric models. This is the Waterloo train station in London, and this was done by Grimshaw Architects, and this is one of the first parametric models. So here was, again, it was some kind of a CAD system which was augmented with scripts to create this parametric model. So it was still a very simple visual interface with some script running in the background which automated all the dependencies between the elements. So you can see that we have some kind of two circles which are bounded together by some dependency on the dependency related to the tangency of each other, and then to some angles related to the, angles measured from some kind of abstract point somewhere in space. And with that parametric model, we are able to change the parameters, right? So we are able to change the radii of those circles and those angles, and then the points which we are relating to. And we are able to repeat that geometry multiple times, changing those parameters. And this is how this Waterloo station was created. So here you'll see that the structure is a long tunnel, and each of those arches is basically a bit different. But because we have one parametric model with different parameters, the relationships stay the same, so the topology of the spatial frame is the same. But because we are changing the parameters, the dimensions change a bit, right? So we have this kind of a tunnel which can be actually turning left. Anyway, so this is the model. So when we talk about the model in our case, we talk about the model which models some geometry in real life. And just to get back to geometry, this is just some surface which I created in one of the projects. And you can see that this is a very flexible parametric model, but it's very simple. Okay? So this is just to show you that once you have one model, once you have some dependencies between geometrical elements, we can actually change the parameters and get different geometries. And that's also how the railway station was created. Okay, so let's get to visual programming. I know that this is a term known to many of you, but I think it has a great revival in the architectural community. And let's talk why. So first of all, those are three languages, VB, C#, and Python, describing some box. Okay, so to describe the box, it's actually Rhino common, so it's a library, it's a geometrical library used in Rhinoceros. So if we want to create a box using this library, we actually have to create a point, and then a plane based on this point, and then using this plane and some dimensions, we can create a box, finally. And the problem with that is that you have three different languages. And architects are not people who like typing at all. As you saw with Ivan Sutherland, for like 50 years we try to skip typing as much as we can. So, and then also another thing is that with the limited time and with the limited resources, we cannot learn all the languages, right? Because you know that every framework and every library has its own nice classes which you would like to use or nice methods. But in terms of architecture, you usually don't have time to learn those new libraries and actually implement them in a one-off project. So that's why we came up with visual programming. And this is Grasshopper. This is one of the softwares used by architects and also engineers and all the AEC industry. So here, instead of, let me go back, instead of those 3 lines of code, we actually have 3 components. And each component actually recreates one of those lines of code. So you have the construct point, which gets the 3 coordinates and creates a point, which then creates the plane, and then finally we have a box. And yeah, so you can see the box on the right, it's Rhinoceros. And yeah, for me as an architect, this is way better, way easier, right? So we'll talk about cliché learning curve, and why do we think that it's better, and when does it how long can we use parametric models as with visual programming till we actually need to code? So that's the topic of this curve. So when we compare the visual programming and the text programming, then we can see that visual programming brings us way faster to some first results. Once I show you this slide, you can probably just create another box and you can already start playing around with different geometries and so on. You probably can find a component which is able to create sphere, and then you're able to create sphere. You don't really have to browse through the SDK and look for methods or anything like that. Once you get the principal mechanics, you basically go all the way forward to being able to create as geometry as you like. When in text programming, you have this slow, I mean, depending on the language and so on, you have this slowly growing skills curve. Because first of all, you have to learn about types, data types, and classes, and object-oriented programming, and then how to display the geometry on the screen. We skip the entire piece of that knowledge just so we get to the thing which already creates geometry for us. And of course, there is a limit to that. So the visual programming, you cannot, I mean, with our software in architectural community, visual programming is not able to compete with regular programming at some point. That's because there is only so many components and you cannot really create them from scratch that easily without actually coding, right? So without actually writing. So yeah, just some nice bulldozer which smashes the code. And yeah, so but the nice thing about The nice thing about visual programming is that it actually teaches you some principles about coding. It teaches you the logical way of thinking. And once you know that, it's way easier to switch to regular programming. So that's what I did. I started with visual programming, and then once I saw that I would like to do something which is not possible with the components which I already have, I actually switched to text, and I learned a couple of languages. So let's just talk briefly about what are the consequences of switching from text to visual programming. The other way around, if we think generally. So first of all, for architects, it's really important. Abstract concepts like a box or like a point or like a plane are made tangible, so you can actually see where is the box. It's not an abstract line of code somewhere. It's actually a piece of visual interface which is responsible for displaying and drawing the box. It's good for teamwork, let's say. Once you have a big visual program, you can actually, distinguish between different parts of the program and label them properly. And then, let's say it's good for teamwork. It's very controversial what I'm saying right now, but let's stick with that. And yeah, so we can very quickly come up with different prototypes of those parametric models with visual programming. And we call those one-off solutions because for every project and even for every concept for every project, you need a separate solution, a separate definition, a separate code, visual code. So it's a rapid software prototyping, and that's very fine because you can actually come up with different prototypes, of course, up to a point, right? So we don't have unlimited resources. We have only some time to come up with different prototypes. But in general, it's way faster to code with those visual programming applications than with regular code. Some examples of the software which we are using. So that's Autodesk Dynamo, Grasshopper, and generative components. That's also very controversial, I will say, but Grasshopper is the most popular in architectural research right now. Maybe not in practice, but maybe you can see why in here, okay? That's just to point you to some kind of UI and UX questions. Okay, so once we know what is a parametric model, so this is a piece of code which actually generates some geometries with some parameters, like the radius of a circle or whatever you think about, we can actually come to how do we use those parametric models. And this is one of the projects in Poland, in Wrocław, and I was glad to collaborate on that with Zięta Process Design. And I created a parametric model for them, some code for the parametric model, which actually enabled them to go through a lot of iterations of the same project. And so they chose one, but they had a variety of options, and it was way, way faster for them to implement them. Then this is a project, the Winton Gallery in the Science Museum in London, done by Zaha Hadid Architects Code Team. And those surfaces which you can see around are actually some implicit surfaces made by equations. So this is also a type of a parametric model in this case. Very mathematical one. But you can see here, and there is a very nice transition to the fabrication part, which we'll get at some point. But you can see that we have this abstract geometry, right? But at some point we can get this geometry and actually try to think about how to actually build that. So this is, this is some kind of a relaxation just to find out the cutouts for the membrane, and that's how it works. And you can see that with this model we don't create one geometry, we create a variety of geometry which we can choose from. So once we know that, we can start to think about how to build that. So that's another thing. You can of course draw a very nice geometry somewhere in the abstract space of the computer screen, but once you want to build it, you have to know that it won't collapse. Okay, so this is one of the research projects which I was working on, and this is a bridge to FAR. It's called the bridge to FAR, and it's a two-layer bridge where each layer is 1 millimeter thick aluminum sheet, and it's incrementally formed by robots. So we'll get there. But before we'll get there, you can see that this is what we do when we want to get the parametric model and actually check how it performs in real life. We actually take the structural performance, which we can also compute with additional libraries. And we can actually find, like, once we have all of those possible solutions, we can actually find the one which is, the strongest one. Yeah? So this is some catalog of all the of different options which we were thinking about, and one of them was actually chosen to be constructed. This is a project by some architects and with Bollinger Grohmann. Bollinger Grohmann is a structural engineering company, but also architectural company, and they are also specialized in optimization. And it's quite of a complex structure. But what I would like to show you here is that this is how the optimization looks. So we have this parametric model, we can adjust the parameters, they build the entire geometry, and then we press the check button. Once we press the check button, we have the displacement, the bending energy, a number of joints, a number of segments, and we can find the one which is the best for us, right? So once we know how that the thing will not collapse, hopefully, we can go to the documentation part, right? Before building something, you always need to print it on paper, or maybe on, have a 3D model on the iPad, or any other tablet. And yeah, so parametric model, once you have a parametric and a digital representation of your geometry that you want to build, you can start playing around with evaluating like simple components which actually constitute the geometry. So you can put more and more detail and more attention to any detail in the structure. And once you have it done, you can automatically print and plot as much documentation as you want. You can have a view of the same joint from 10 sides, right? And this is one of the projects which is well documented. I would recommend you to visit the website seen here, and there is a webinar actually describing the entire project very well. And yeah, you can see that this is a complex piece of geometry. This is just a sample. It's actually done already, but I would really recommend you to see the website. And this is how the model looks when it's actually on the computer screen, right? So it's actually already being, it's actually completed. The project is already completed, but I just wanted to show you this geometry and some dumb statistics. And now relate back to the first slide about the Eiffel Tower, right? So 500 people drawing the Eiffel Tower. In this project, there was 4 people actually managing the entire geometrical model. So here we have like 25,000 panels, and I know like fastener count is like 5 million. I have those notes noted down. Total parts is like 1.5 million parts, right? And every part is basically unique because of the twisted shape of the structure. You can see that maybe there are some regularities, but especially in the middle, there's completely irregular geometry. Okay, so once we have the documentation, then we have all the drawings. We go to the manufacturer and we ask him to do it for us. And we can of course think about classical fabrication and all the carpenters and all the people actually involved in the process. But I would like to point you to this kind of a new, still emerging methods of fabrication, which is like robotic fabrication and CNC fabrication. So this is again the bridge, and here you can see 2 robots actually incrementally forming incrementally forming the sheet of metal, and the second robot is behind, so it's only the white top of it, which you can see. Yep. So yeah, once we had the model, we can actually draw the toolpaths and just make the robots fabricated. This is another project by a school in Barcelona called IAC, and it's using a robot to extrude clay and and print those complex kind of bricks, if you want to call them that way. And it's being exhibited right now in Barcelona. And this is just another. I don't have any movie, unfortunately, but I would, if you note down the name of the project, you can probably find some. So you can see that this is just another way of fabricating with robots, and it's also possible thanks to parametric models. So then each brick is actually a bit different, and when you actually extrude them with the robot performs different toolpaths every time. Then once we have fabrication, we have some parts, and we get to the assembly. So once you have the parts, you want to put them together. And maybe this is not the best example, but this is one of the nicest examples of assembly. This is a school in Stuttgart. Those are actually two departments, ICD and ITKE. And they created this pavilion 5 years ago. They create the pavilion every year, but this one shows really well how the robots actually can fabricate and assemble the pavilion. So, of course, this is a medium-sized structure, it's a pavilion, so it's like a 5 by 5 meters, maybe a bit bigger. But with that kind of setup, you can basically create as many of those as you want, and you can treat it as an element of a bigger structure. Okay, so limits. Once you've seen the examples of parametric modeling, structural engineering involved in the process, then fabrication, assembly, and documentation. Now we have to talk about the limits of parametric models, and there are some. So first of all, code complexity. And this is literally, or figuratively, I'm not sure about the word right now, but this is spaghetti code, right? And you can actually see the spaghetti part. So code complexity, at some point, because of like the nature of visual programming, we get to the limit of the things which you can actually cope with. And at some point, the software, the program which we are coding is becoming so complex that you cannot even change anything anymore. Or if you do, it's actually faster to recreate the entire thing from scratch, and on the way of recreating that, create some part a bit different. The other limit is, which I would like to just talk about, is the one-off can only do that much, which is one-off software can only do that much in terms of the limits of costs and limits of time. And of course, having those one-off parametric solutions is very expensive. So you have to have the right people. You have to have a lot of research done before, and you have to have a lot of skills a particular skill set to complete this project. So high cost, basically. Then I have another 2 points. Robots are hard. This is a very generic statement, but robots are hard means that all the robots which you saw, all the software which is running those robots, this is actually a definition which runs one of the robots for the bridge project. And when you see that panel, it looks like a complex geometry, but it is not. If you think about it, it's just a metal sheet. But this is how much code you need to create to actually fabricate that. There's a lot of real-world problems which we have to solve, like collision detection, the speed at which the robot can actually move, the properties of the material, finally, because, for instance, in the incremental sheet forming, you cannot push too fast because it will actually tear the metal. So yes, robots are hard that way. There is a lot of research to be done, and it's actually quite an ongoing thing. And then another point is material simulation is hard. So when I'm talking about pushing the metal through and tearing the metal, the material simulation and all the methods, which is like finite element analysis, are really hard and really slow. So this is also something which we are in the academia still working on, and this is still an ongoing thing. Now the future. So what is the future of all of that? I have this point written down, which is new type of modeling paradigm. So, however abstract it sounds, but basically we can think about the architect not being responsible for one building, but rather for a parametric model which can generate a variety of buildings. And then the architect's role is first to create this parametric model, and then to actually choose from the entire solution space the ones which he or she likes. So this is a new way of thinking about architecture, and about not only architecture, but this also applies to other creative industries, which also use this kind of modeling software. Currently, there is some research done on machine learning. So once we have the parametric model and all the geometry associated with that, we can actually think about machines performing some of those tasks. So just as I said, once you have the model and the entire solution space, maybe the machine can actually perform the selection of the models which you actually like. And then, of course, we talk about the robots all the time. And there is actually a separate conference just on robots in architecture. Because it's a very, very tough problem to cope with. And then finally, we think about drones. So this is more about the urban scale of architecture, but also about smaller scale, maybe one building type of projects. This is a project by Anemone from Barcelona, and this is a drone which currently flies above plantations of pineapples in South America. And it uses some IR sensors to actually see what is the current condition of the pineapples, and it tries to look for diseases. So it prevents the diseases from spreading on the entire field and actually ruining the crops. And here I'm showing you, a very agricultural application. But you can think about it in a way that we can use the same drones and the same software, the same hardware to fly above the cities and measure different qualities of the city, like the pollution of air or maybe the traffic congestions. Okay, so this is another future thing because it's still it's still hard to fly with the drone above the cities legally. There is a lot of legal problems about what happens if the drone falls down on the ground and actually destroys something, for instance. And maybe now about the conclusions. So, yeah, coding currently is, let's say, integral part of the architecture in one way or another. It means that some offices already have research groups which try to employ the computational methods in architecture, and it will be more or less visible. So. You sometimes, I showed you really a variety of really complex buildings, but it can be also applied to very simple buildings. Just because you have this possibility to create hundreds of or thousands of solutions, this means that even with a simple design, you might want to do that. The other conclusion is that we need more coding people. So. There is still a surge of coding people in the industry, and some schools start to apply, start to teach the students, the architecture students, coding, visual programming or just regular programming. But we have still a couple of year gap to actually catch up with the demand. Yes, so. And another conclusion is that parametric modeling and this kind of visual programming, it actually influences the architecture itself. So it actually influences us as architects in the way we think. So we have to think logically. We cannot. We can, but we cannot. In this context, we cannot think in a very artistic and non-bounded to reality way. We still can, but it cannot be the part of the programming part, of course, right? So it actually directly influences the thinking behind architecture. So can we imagine architecture without coding? I don't think so anymore. So I think that the speed up which we saw coming from the Eiffel Tower drawing 500, having 500 people drawing the entire thing, and then 4 people drawing the Morpheus Hotel, this shows that there is no way back, right? We already cut the cost so down and cut this time and expenses to draw those complex geometries so much then that I think there is no way back. So I think that we have to actually put a lot of effort into getting a lot of, more people involved in this process. And I would like to thank the companies which sourced me with some of the materials. And thank you.